Okay, time to go after another one. So we have an electron, and we have a nucleus of lead, which has got quite a large charge. And so we have an E minus, and the Q of the E is equal to negative 1.6 times 10 to the negative 19 coulomb. And we have charge of the lead equals, oh, they did the multiplication for us, nice. Times 10 to the negative 17 coulomb. We treat them as point charges. And, so we have some V0 of E is equal to 0. Yeah, it's at rest. Okay. And what else? R0 equals 1.00 times 10 to the minus 10 meters. Oh, that was nice. So alright, so we can draw our little sketch here. And, well, we can make that a little longer because who knows what's going to happen. And, oh well. Okay, so we got the lead. We got E minus, and we have our R sub 0. How much work would you have to do to move the electron to a distance 5? Okay, so we there's no change in KE, and it actually didn't ask us, just asked how much work. So work equals the negative delta U. It's not that's super big of a deal. So U is equal to KQ1 Q2 over R. So it says now that R, we'll call it R sub A for part A, equals to 5.00 times 10 to the minus 10 meters. Okay, so let's just calculate the two U's, delta U, right, it implies. So U sub 0, excuse me, is equal to, well, we have the equation, so we're just going to 8.99 times 10 to the 9th. And, in fact, I think I'm going to calculate first the numerator, because I'm going to use it over and over again. And so minus 1.60 times 10 to the minus 19 coulombs times 1.31 times 10 to the negative 17 coulombs. And so let's get the trusty calculator out. .99 E9, enter. 1.6 E negative 19 times, and 1.31 10 to the negative 17 times. So that's quite a small number. Equals 1.88 times 10 to the negative 26. And, wow. Yeah, the answer has to be in Newton meters. I think, yeah, this is in Newton meters squared because we're going to be dividing by meters. Okay. Wow. Okay, so I'm going to go up to the next page, and then I'm going to say then U sub 0 equals 1.88 times 10 to the minus 26 Newton meters squared divided by 1.00 times 10 to the negative 10 meters. Well, that's convenient, huh? 1.88 times now, so when it's in the denominator, you add it to that, so that's going to be negative 16 joules. Oh, 10. And then U of A is going to be equal to 1.88 times 10 to the negative 26 Newton meters squared divided by 5, right? Times 10 to the minus 10 meters. So it's just the answer divided by 5. So 5 goes into 18 3 times. Carry, there's a 3 left over. So 7. Yep, 7. So that's 30. So it's 3 left over. And oh, it goes in exactly. And so this is going to be 0.376. I gotta try that and see how good I am still. 1.88, enter, 5 divide. Yep, you got it right. And then once again, times 10 to the minus 16 joules. And I'm going to leave it like that because I have to subtract them. So we have, let's be careful here. These are both negative numbers because this is a negative number. So we have the final position is negative 0.376 times 10 to the minus 16 joules. And I need to subtract the final, the initial potential is negative 1.88 times 10 to the negative 16 joules. So we see that that means we're going to add the two things together. Enter 1.8, oops, 88, and so we're going to add plus, oh, but I forgot to enter the first number as a negative number. So it's 0.376, enter, then 1.88 plus. So I end up with 1.50 times 10 to the minus 16 joules. And so delta U is positive, and then the work equals negative delta U equals negative 1.50 times 10 to the minus 16. And that is, now it said how much, and we know that this is the work of the electric field. And so these are attractive. And so that means it asked how much work would you have to do? So we have to, so we're doing we're pushing against the electric field. So this is from the E field. So what this says is that we have to do a positive 1.50 times 10 to the negative 16 joules. We do that, and that makes sense because it means now that the potential energy is increased because we've pushed against the electric field, and they naturally want to come together. And you know, even if you didn't remember the negative delta U part, you see that the change in potential energy is positive. And since we have to push against the electric field, that means that we're doing the work, we're doing the positive work, we're increasing the potential energy. It's great, okay? Now, even if the two potential energies were negative, you would have ended up with a positive number there. Oh, wait a minute, they are both negative, duh. But you just see that it works out so that we can, and that we end up with a positive delta U, and that makes sense because the potential energy of the particle is increasing. Okay, so if we release the particle from the position in A, which actually means little a, I remember that. Let's see. So I want to keep this diagram. Yep. So we're going to copy this. And we're going to bring it to this other side here. And so now so this 5 times, so we don't have the amount of room to draw that. So R of A, and now it says release from rest, right? Yeah, because it never was moving. So we'll call it point A. V of A once again equals 0. and R of A equals to 5.00 times 10 to the minus 10 meters. And if you release what will be its kinetic energy when it becomes, wow, quite a small number. So RB equals 8.00 times 10 to the minus 12 meters. So this becomes this becomes conservation of energy because it's only being acted upon by the conservative force of the electric field. I let go of it. And so that means that K, the kinetic energy at A plus the potential at A have to equal the kinetic energy at B plus the potential at B. And we know that this is equal to 0 right off the bat. So KB is going to equal UA minus UB. Not surprisingly, it's the change in well, not quite, right? See, it's not delta U in a way because B is the final position. And it's negative delta U, right? Because if I want the kinetic energy to increase, then the potential energy has to decrease. And that's going to happen when it's only a conservative force. Okay, so we already know what is the potential energy at A is 1.88 times 10 to the negative 16 joules. So potential at B is going to be our numerator. So U of B is going to equal the numerator over R sub B, and that's going to be negative 1.88 times 10 to the minus 26 divided by 8.00 times 10 to the minus 12, right? 2 orders of magnitude. Yep. And meters, that's Newton meters squared. And so that's going to equal, okay, 1.88. That's change sign. E26. Enter. 8 times 10 to the minus 12. Divide. And of course, this is a negative number. I forgot to transcribe that. And this is a minus 2.35 times 10 to the minus 15. So we have negative 1.88. Yep. Right, U of A times 10 to the minus I lost it already. 16, and we have to subtract from it something that has an exponent of 10 to the minus 15. And yeah, it's bigger. I expect it to be bigger. So to make it 10 to the minus 16, we got to make it, we got to move the decimal place over. 1 times 10 to the minus 16. See, if we move it over to the right, that means to get the same number, we have to move it over to the left more. So it becomes negative 16. And when it's negative, we're moving it over to the left. So then what we're doing now is we have a positive 23.5 times 10 to the negative 16. And I put joules, that's not, I mean meters, that's not correct. And we're subtracting from it 1.88 times 10 to the negative 16 joules. And so 8 from 10 is 2, 8 from 14 is 6, and then 1 from 22 is 21, and times 10 to the negative 16. And so we make it 2.16 times 10 to the negative 15 joules. And it's a positive number, but we have to hit it with the negative sign because, well, the kinetic energy actually is positive. Right, sorry. The kinetic energy is positive, so Ka then is, and it has to be positive, don't forget. The Kb then equals that. Neat. Coolio, right? So, right, you have to always, if the kinetic energy increases, even if the kinetic energy decreases, it always has to be a positive number. So that's kind of cool that worked out. Okay, so let's see what C says. Yeah, so now I give it a velocity. And so let's say we have Ka plus UA. So first we need to determine what that is. And Ka is no longer 0. And this is where you're supposed to have the mass of the electron in your notes, huh? And so I know it's 10 to the negative 31 kgs. So I'm going to cheat here, and I'm going to look it up. I suppose in an exam you could get away with this. Let's see. In an exam. But, you really should have this in your notes. I better make sure and say that in class. Oops. Well, I'm just reading that. They just hired a new coach for the women's soccer, and now they just got Pochettino for the men, but they're going to pay him much more money. That is rude. Especially since the women's team wins so much more and makes so much more money. Okay, so then Ka is equal to 1/2 mv squared is equal to 1/2 of 9.11 times 10 to the minus 31 kgs times, let's see what they said, 1.5 times 10 to the 7th. So now how do we, VA equals 1.50 times 10 to the 7th. Wow, that is a significant fraction of the speed of light. It's 1/20th. Okay, so it's 5% of the speed of light. Meters per second. So 1.50 times 10 to the 7th meters per second squared. Where is it? Squared. Okay. So right off the bat, this is going to be 15 times 15 is 225, and that's 10 to the 14th meters squared per second squared. So we can just type that in, 2.25 E14, enter, 9.11 e to the negative 31 times, and then 1/2, 0.5 times. So this is 1.02 times 10 to the negative 16 joules. And so we remember that the 1.88 times 10 to the negative 16, negative 1.88. So U of A equals negative 1.88 times 10 to the negative 16 joules. So E total equals to Ka plus Ua is equal to 1.02 times 10 to the negative 16 joules, and minus 1.88 times 10 to the negative 16 joules. And yep. So that means that E total is less than 0. So the electron will come to rest somewhere, and then it will come back. Okay. And right, so its final speed is, well, in a way, infinity when it crashes into the lead nucleus. But where will it turn around? So that means that Ka plus Ua equals, let's say, Kc plus Uc. And this is going to be 0. And we already know that U of C is going to equal to, we didn't do the subtraction, but it's negative 0.86 times 10 to the negative 16 joules, because that's when I do this subtraction up here. So I suppose we should say equals 0.86 and we have to add another sig fig times 10 to the negative 16 joules, and it's negative. And then that equals to the numerator over R sub C so R sub C equals negative 0.86 times 10 to the minus 16 over the numerator, joules. So at this point, you know, and they're both negative. Wait a minute. Yeah, they're both negative numbers, don't forget. So you're going to get a positive number, which is good. It's negative, ridiculous. Oh, there it is. 1.88 times 10 to the negative 26 Newton meters squared. And it's going to be divided by, nice, it's going to be divided by meters. Oh, I did it wrong. Okay, wait a minute. Let's get rid of this. You know, the numerator is underneath. Yeah. No, yeah, numerator is on top. Whoops. So let's delete that for now. So so the UC and the RC, we're going to switch places. So it's going to be numerator divided by U sub C. Okay, and that's what we want because this is negative 0.86, and we do expect it to be, if it had been the other way around, I think it might have gotten smaller than 1 times 10 to the 10th, and we can't have that. Times 10 to the minus 16. And remember, a joule is a Newton meter, so we're left with meters on top, which is really nice. And I'm going to, you guys know how to punch into calculators. That looks like it's about 2.5 times 10 to the minus 10. See if I'm right.